A very good morning to all of you. Dear students, I welcome you all to this chemistry session. We have already gone through 15 group elements in P block. Hope you all have seen the videos and made points and good notes which will help you during the annual examination. We also have started group 16 elements, the oxygen family, and you are familiar with the occurrence of group 16 elements starting from oxygen to polonium, and then you also have studied some of the atomic properties and their variation trends down the group. Now, you also have studied physical properties too. Then now we will start with the chemical properties. In the same way we will go as we have done with group 15 elements. Now, chemical properties. We start with the oxidation states. Oxidation states, as you know, group 16 elements have NS2, NP4 configuration in the valence shell. So, there are two lone pairs, one in S orbital and one in P orbital. So, there are two lone pairs and there are two unpaired electrons in its valence shell. So, they exhibit variable oxidation states because, or actually they need two more electrons to become 8 octet and become stable. But depending on the mode of formation, conditions and the elements with which they are combining, they exhibit variable oxidation states. Now we will see one by one. The oxygen exhibits oxidation states of -2 and -2 oxidation state, that is gaining 2 electrons to become stable, is the most common oxidation state of oxygen. Normally in all the compounds it exhibits -2 oxidation state, that is because of very small size which helps it to attract the electrons, and therefore all the oxides, especially oxides, are ionic in nature, or if there are covalent bond they are polarized because oxygen is more electronegative and draws the electron towards itself, and therefore it exhibits -2 oxidation state in common. -1 oxidation state is also possible for oxygen, and you have studied this in redox reaction. The points or the conditions you have to remember where -1 is observed in peroxides, for example hydrogen peroxide, sodium peroxide. So in peroxides the oxidation state of oxygen is -1. Then oxygen is highly electronegative. Then how does it get positive oxidation states? That is only when it reacts with the more electronegative element than itself, that is only fluorine. So it gets positive oxidation states with fluorine because fluorine is more electronegative and draws the electrons, and you have two compounds, O2F2 dioxygen difluoride and oxygen difluoride, where the oxygen gets +1 oxidation state in O2F2 and +2 oxidation state in OF2. That is about the oxidation state of oxygen. Then coming to the next 3 elements, sulfur, selenium and tellurium, they normally exhibit -2, +2, +4 and +6 oxidation states. And polonium does not exhibit -2 oxidation state because it is a metal, and due to large size it cannot accept the electrons easily, and therefore it does not show -2 oxidation state. It shows only +2, +4 oxidation states. +6 is not present. I will give you the reason now. So these are the common oxidation states. Now we will see the stability of these oxidation states. Of course, the stability of -2 oxidation state, gaining of 2 electrons, decreases down the group. This we have also explained in the 15 group elements, because with the increase in the size, gaining 2 electrons becomes difficult. The nucleus cannot hold the electrons tightly when the size becomes larger or bigger and bigger, and therefore with the increase in the size from oxygen to polonium, the -2 oxidation state becomes impossible, and therefore the stability of -2 oxidation state decreases down the group. That is why polonium does not show -2 oxidation state, it becomes a metal. And then the stability of +6 oxidation state. The stability of +6 oxidation state also decreases down the group. The reason you have studied the NS2 electrons are reluctant and they do not participate in chemical bonding. They keep themselves away from bonding. They are not coming for bonding. So the remaining 4, therefore, when you move down, the stability of -2 decreases and +6 also decreases because of inert pair effect. And therefore, as the stability of +6 tendency or stability goes on decreasing down the group, the stability of these elements to show +4 oxidation state goes on increasing. So +4 oxidation state stability goes on decreasing down the group. Therefore, there is no +6 for polonium, it becomes only +2 and +4. And oxygen, as I have already told you, exhibits only -2 oxidation state in all the compounds except for these -1, +1 and +2 with fluorine. And all the compounds in +4 oxidation states are normally with highly electronegative oxygen atom. All these elements exhibit +4 oxidation states normally with oxygen, and +6 oxidation normally they show with the fluorine, which is the highest electronegative element. And both these compounds or bonding in these compounds are covalent in nature. So these bondings are covalent in nature. So this is about oxidation states of group 16 elements. Next, as we have done in the group 15 elements, next we will see the reaction of group 16 elements with hydrogen. So they form hydrides of the type, general formula H2E. H2E, where E can be any element of 16 group, oxygen up to polonium. So we will take these compounds one by one, hydrides. So when E is oxygen, it is H2O, then H2S, then H2SE, and this is H2TE. So this is hydrogen monoxide, we say. This is hydrogen sulfide, hydrogen selenide, hydrogen telluride. We normally avoid the study of polonium because, as I have already told you, it is a radioactive element, very rarely formed, and we do not use these in common reactions. So now coming to the properties of these hydrides. Now the bond length, as the atoms become bigger from oxygen up to tellurium, the bond length of the element and the EH, OH bond or SH bond or HSEHT, the bond length goes on increasing. As the bond length increases, the bond gets weakened, and therefore the bond dissociation enthalpy also decreases. We need more energy to break OH bond than tellurium hydrogen bond. So the breaking of bond becomes easier, and therefore the thermal stability decreases as we move from water to hydrogen telluride. And therefore we can easily separate hydrogen and tellurium compared to hydrogen and oxygen. And because of the dissociation energy decreasing from water to hydrogen telluride, the acidic character of these hydrides goes on increasing. So this is one of the very important question which has come repeatedly in the annual examination. Make a point of it. Why hydrogen telluride is more acidic than water? So this is the type of question, or any question on this concept. you have to tell from H2O, when we reach H2 telluride or hydrogen telluride, the bond dissociation enthalpy decreases and therefore acidic character increases. Therefore, water is the least acidic. This is little more acidity increases, and among these the most acidic is H2TE. And when the water does not act as a reducing agent, except water, all these act as reducing agent by providing hydrogen for reduction purpose, and except water, the reducing character also increases because breaking of bond becomes easier. Therefore, in this compound you can separate them easily compared to these two. So this is the most powerful reducing agent among the three, or the stronger, and this is the weak reducing agent. So the reducing character also increases as you move down. And then there is one more property I want to discuss about water. Is in water, you have studied last year that because of high electronegativity of oxygen and very small size, it attracts the electron pair and the covalent bond gets polarized, and when these develop partial charges, the negative part, oxygen of one water molecule attracts the hydrogen of the other molecule, and this is called intermolecular hydrogen bonding, and due to which the water molecules come nearer and therefore their boiling point increases. So if there was no hydrogen bonding, imagine H2O would be a gas, not a liquid. Then imagine what would be the situation if H2O was not liquid, it was gas in the nature. Okay, now H2O molecules associate themselves and there the boiling point is higher. Therefore, all these are gases, but H2O is a liquid owing to the hydrogen bonding, extensive intermolecular hydrogen bond present bonding in water molecule. So water is a liquid, and H2S or H2Se or the telluride is they're all gases. So we have to answer. Suppose you get a question like this: why H2O is a liquid, H2S is a gas? Oxygen is small and highly electronegative and is able to polarize the bond, and hydrogen bonding develops, whereas sulfur or in other compounds, as the size increases, their electronegativity is less and they cannot polarize the bonds. Therefore, there is no hydrogen bonding. So this is about oxidation states and reaction with hydrogen. Then we will see the reaction of these group 16 elements with oxygen. So with the oxygen, they form two types of oxides, EO2 and EO3, where E is the group 16 element. So EO2 and EO3. For example, SO2 sulfur dioxide and SO3 sulfur trioxide. Among these, both are acidic in nature. So both of them produce acids in the air when they are put into water. So both the oxides are acidic in nature. O3, which is considered as oxygen dioxide, OO2, like O3, and SO2 are gases, and the remaining two, selenium and tellurium dioxide, are solids. Okay, then these act as reducing agents, or these EO2 act as reducing agent, and the reducing character decreases when you move down from sulfur to tellurium. The reducing property decreases down the group. For example, SO2 is a reducing agent, whereas TeO2 is oxidizing agent. Sulfur, the reducing character of the dioxides decreases down the group. Sulfur dioxide is reducing agent, whereas tellurium dioxide acts as oxidizing agent. So this is about reaction with oxygen. Next we will see the reactivity with halogens. These elements form different halides using their different oxidation states. Example, they form hexahalides, they form tetrahalides, they form dihalides, and they also form monohalides. Okay, so now among all these halides, the stability of the halides, if you see which halogen gives the most stable compound, in that we can see the fluorides are highly stable or highest stable, then followed by chlorides, then bromides, and then iodides. So fluorides are more stable, then chlorides, or you need not put this also, you can say fluorides are more stable than chlorides, than bromides, and iodides come at the end. So the compounds of these elements with the fluorine are the most stable compounds. And when you consider the hexahalides, only hexafluorides are stable. Only hexafluorides are stable. All these have sp3d2 configuration with the octahedral geometry. Their structures are octahedral and they have sp3d2 hybridization, and all these hexafluorides are gaseous in nature. They are all gases in nature. And SCF6, sulfur hexafluoride, you have studied about the hybridization last year. Okay? So in chemical bonding, so sulfur hexafluoride is extremely stable or exceptionally stable due to steric considerations factor. So SF6 is exceptionally stable. Next we will take EX4, that is tetrahalides. If you take tetrahalides, SF4 is a gas, SEF4 is a liquid, and TEF4 is a solid. SEF4 is a gas, SEF4 is a liquid, and it is the tellurium tetrafluoride is a gas. And all these compounds are sp3d hybridized. Their hybridization is sp3d. So actual structure should be trigonal bipyramidal. But due to the presence of a lone pair of electron, their structure, because of the lone pair, the structure becomes seesaw geometry. They obtain seesaw geometry, which seesaw is like what the children used to play in the parks, like this. Okay, so there is a lone pair here, and this is metal. So the X. So they slightly bend due to the repulsion exerted by the lone pair according to VSEPR theory. So this is about the tetrahalides. Next, coming to dihalides, EX2, except selenium, the others form dichlorides and dibromides. For example, they form dichlorides and dibromides with the sp3 hybridization. These dihalides have sp3 hybridization, and therefore the expected structure is tetrahedral. Expected structure is tetrahedral, but due to the presence of a two lone pair of electrons on these elements, atoms, the structure becomes bent. The structure becomes bent like water. The bond angle also decreases from what is expected of through tetrahedral geometry. And they also form monohalides which dimerize, are in the dimerized form. For example, S2Cl2 or S2Br2, Se2Cl2. So monohalides are normally in the dimerized form, and these dimers normally undergo disproportionation. So this is disproportionation of diselenide dichloride, disproportionate to give tetrachloride, and selenium is formed. So these are some of the things about the reactivity of group 16 elements with halogens. Next we will see the anomalous properties of oxygen. So oxygen, all the second period elements in the respective groups show some distinct or different properties, which we refer to it as anomalous properties compared to the properties of the other elements. So ಸಣ್ಣ ಸೈಜ್ನಿಂದಾಗಿ ಇದನ್ನು ನೀವು ಗ್ರೂಪ್ 1ನಿಂದಲೇ ನೋಡ್ತಾ ಬಂದಿದ್ದೀರಿ. 1, 2, 13, 14ರಲ್ಲಿ 15ರಲ್ಲೂ ನೋಡಿದ್ದೀರಿ. ಎರಡನೇ ಪೀರಿಯಡ್ನ ಎಲ್ಲ ಮೂಲವಸ್ತುಗಳು ಉಳಿದ ಮೂಲವಸ್ತುಗಳ ಗುಣಗಳಿಗಿಂತ ಸ್ವಲ್ಪ ಭಿನ್ನವಾದ ರೀತಿಯನ್ನು ತೋರಿಸ್ತವೆ. ನೈಟ್ರೋಜನ್ ಆಲ್ಸೋ ಐ ಹ್ಯಾವ್ ಎಕ್ಸ್ಪ್ಲೈನ್ಡ್ ಮೆನಿ ಡಿಫ್ರೆನ್ಷಿಯೇಟಿಂಗ್ ಪ್ರಾಪರ್ಟೀಸ್ from the other compounds, that's called and other elements, anomalous properties. Once again, you know what are the reason for the anomaly exhibited by oxygen. The reasons are: 1, due to small size, and then high ionization enthalpy, due to which they have very high electronegativity. And do you remember the fourth one? Yes, it is absence of d orbitals. So which are the properties which are different from the other elements, that we'll see. Normally oxygen is a gas and all the others are solids. Oxygen is a gas and others are solids. Because of anomalous properties of oxygen, all these, oxygen combining with hydrogen, water is in the liquid form. That is due to the small size of oxygen atom, which is highly electronegative. Therefore, due to hydrogen bonding, it exists in the liquid form. Whereas the other hydrates starting from sulfur to tellurium are gases without hydrogen bonding. They are not able to form hydrogen bonding because of the larger size. And then because of the absence of d orbitals, the maximum covalency of oxygen is only 4, but usually it forms only 2 bonds. Covalent bonds of oxygen is normally only 2, but other elements can expand their covalence beyond 4, that is 5 or 6, especially in oxides or fluorides, forming more than 4 covalent bonds using the d orbitals. So the maximum covalency of oxygen is only 4 due to the absence of d orbitals. This is about the anomalous properties of oxygen, which is quite different from the other elements of the group. We can also consider Oxygen exists as a gas and all the others are existing as solids. So these are some of the anomalous properties. Next we will start with the preparation properties and uses of the element oxygen, that is dioxygen. O2, it has a double bond by the sharing of two electron pairs between two atoms, and therefore bond enthalpy is high. Therefore oxygen is present in the atmosphere without any reaction, but it reacts only under temperatures. So dioxygen, how can we prepare dioxygen in the laboratories? Method 1, preparation method by heating some chlorates or permanganates or nitrates. So these salts, chlorates, permanganates or nitrates, on heating give oxygen. For example, this is potassium chlorate, which when heated to high temperature gives potassium chloride with the evolution of oxygen gas. So potassium chlorate on decomposition when heated to high temperature gives potassium chloride and oxygen gas. But this is very slow reaction. To enhance the speed of the reaction, we use a catalyst, manganese dioxide. Remember dear students, this is one more very important concept about which sometimes the question is asked in the first section itself. Name the catalyst used in the preparation of oxygen, or the role of MnO2, what is the role of MnO2. So you have to finally remember this equation where potassium chloride decomposes to give potassium chloride and oxygen in the presence of manganese dioxide. So the second method, by heating or decomposition of certain metal oxides, and these metal oxides in which the metals have highly positive standard reduction potential, for example silver, mercury, etc., or higher oxides of certain metals. So this is another method. I'll give you the examples. Silver oxide, when heated, easily it decomposes, because this is not a highly stable oxide, it's quite unstable, easily decomposes by heating. It gives silver plus oxygen gas. In the same way, mercuric oxide on heating gives mercury plus is oxygen. So these are unstable oxides. Or higher oxides of some metals, for example Pb3O4 on heating easily gives lead monoxide and oxygen gas is given out. In the same way, PbO2 dioxide can also be heated to give monoxide of lead and oxygen gas. So these are some of the methods. And then we also have another method, the third method, by the decomposition of hydrogen peroxide. So hydrogen peroxide. So when hydrogen peroxide is not a very stable compound, it also, even in the presence of dust particles or any metal acting as the catalyst or even manganese dioxide, it decomposes to give water with the evolution of oxygen gas. So hydrogen peroxide, if it is kept for a long time also, slowly oxygen gets evolved in it. So in the presence of catalyst, the evolution of oxygen or the decomposition will be faster. So we can use any metal catalyst, or even manganese dioxide can be used as catalyst in decomposition. Next we will see the fourth method. There is abundance of water in the earth. So from water, how do we prepare from water? All of you know this method. Pure water added, because pure water is a non-conductor of electricity, we acidified it a little, very dilute acid. When electricity is passed through water, it decomposes to give hydrogen gas and oxygen gas. Hydrogen is released at the cathode and oxygen is given out at the anode. So this is one more method, and the fifth method is from air. From air, where there is 20.946% of oxygen. From the air, it is like how we have separated liquid or nitrogen from air. The first air is dried, freed from carbon dioxide, and then the purified air is liquefied. So the air is first liquefied, and then on fractional distillation, liquid air, the temperature is slowly increased. Liquid nitrogen boils out first at 77.2 Kelvin, and then the temperature is slowly increased to 90 Kelvin. Liquid oxygen boils out. So this is how we separate oxygen from the air. So these are some of the methods in which we can prepare oxygen. Next, coming to the properties of oxygen, you know very well it's a colorless gas, no smell. It is soluble in water. So if you come to the physical properties, it is colorless, odorless, soluble in water to the extent of 38.8 cm cube per 1 liter water, or 1000 cm cube of water. But this dissolved oxygen is enough to maintain the aquatic and the marine life. So this is 1, this is 2, solubility in water. Then it forms 3 stable isotopes. It has 3 stable isotopes: oxygen 16, oxygen 17 and oxygen 18 with these mass numbers. And one more thing you have to remember, O2 is paramagnetic. The paramagnetic property of oxygen is explained by using molecular orbital theory, which you have studied already in the chemical bonding lesson in the first year. So these are the physical properties. Next we will discuss the chemical properties. Now you know very well, oxygen simply, even if it is a supporter of combustion, it does not simply burn itself. It has a double bond with bond enthalpy of 493.4 kilojoules per mole. The bond enthalpy of oxygen is this much. So all these reactions occur once you initiate the burning. Combustion is spontaneous, but we need initiation to break the bonds. So in the chemical properties, oxygen reacts with all the metals, non-metals, except for noble metals like platinum or gold, or noble gases. It reacts with almost all the compounds, and the reaction of oxygen with anything is exothermic. So combustion delta H we always write negative. So carbon burns in oxygen and gives carbon dioxide. Phosphorus burns in oxygen to give phosphorus pentoxide. Then calcium burns in oxygen to give calcium oxide. Aluminium burns in oxygen to give aluminium oxide. Then compounds like zinc sulfide, the sulfide ores when roasted in oxygen, they give their oxides and sulfur dioxide gas. Organic compounds, all the hydrocarbons and the organic compounds react or burn in oxygen, and all these reactions will give a lot of energy. So in thermochemistry you have come across all such equations where we have written high values of enthalpy of combustion for the burning of hydrocarbons, and the burning of the sugars and the food materials we have taken in our diet with the oxygen inhaled gives energy, because of which our body temperature is maintained and all the metabolic activities are done. So methane plus oxygen gives carbon dioxide. And some of the compounds are catalytically oxidized. For example, 2SO2 plus gives 2SO3. This is in the presence of vanadium pentoxide catalyst, and hydrogen chloride is also oxidized in the presence of catalyst CuCl2 into water and Cl2. So there are some of the reactions which need only temperature, and some of the oxidation reactions need catalysts like this. So next, what are the uses of oxygen? You know very well for what oxygen is used. The very life is dependent on oxygen. We need oxygen for respiration purposes, and then oxygen is used to burn acetylene gas in cylinders. Acetylene flame is used for welding of metals, especially iron, and then oxygen cylinders are used in the hospitals and high altitude mountaineering or flying purposes, even under the sea. Submarines, they also carry a cylinder of oxygen. And then combustion of fuels, of course all these engines work on this basis. They are oxidized, the petrol, diesel or whichever fuel we take, they are oxidized in the presence of oxygen of the atmosphere, and hydrazine in oxygen gives a lot of thrust in the rockets. So all these are the uses of oxygen. Oxygen is one of the reactants for oxidation in many of the industrial processes also. So that is about oxygen. Next we will see about oxides and their classifications. What are oxides? Oxides are the binary compounds of oxygen with any other element. Any element combined with oxygen, that product is called as an oxide. Okay. So there are one element some of the elements like aluminum or sodium form only one type of oxide, and there are many elements which form more than one type of oxide. For example, hydrogen monoxide, peroxide. Nitrogen forms 5 or 6 types of oxides. So some of the elements form in their different oxidation states, they form different oxides. And in the oxides, some are simple oxides. For example, calcium oxide, nitric oxide, magnesium oxide, all these are simple oxides, and some oxides are in the form of mixed, that is Pb3O4. This is a mixture of 2 oxides, and this is ferroso-ferric oxide. This is also ferroso-ferric oxide is also a mixture of ferric oxide and ferrous oxide. That is about simple and mixed oxides. Then how do we classify these oxides? The classification, they are classified into acidic oxides, then basic oxides, amphoteric oxides, and neutral oxides. So we have come across all these oxides in one or the other reaction. So what are acidic oxide? Any oxide which when put into water produces an acid. Any oxide which when dissolved in water gives you an acid is an acidic oxide. For example, Sulfur dioxide when put into water gives sulfurous acid. Sulfur trioxide gives sulfuric acid. Phosphorus pentoxide gives phosphoric acid. So examples are sulfur dioxide, sulfur trioxide, carbon dioxide, nitrogen dioxide, phosphorus pentoxide. All these produce acidic solutions in water. So normally you can observe non-metal oxides are acidic in nature. Non-metal oxides are acidic in nature. But some of the metal oxides in which the metals have their high oxidation state, +7, highest oxidation state, like here it is +6, it's +7, such compounds also exhibit acidic properties. Next, coming to basic oxides, this is the opposite of this. These are the oxides which when put into water will give you a basic solution, hydroxide. So calcium oxide when put into water gives calcium hydroxide, which gives you OH minus ion. It's basic in nature. Normally all metal oxides are basic in nature. So metal oxides are basic. For example, calcium oxide, aluminium oxide, potassium or sodium oxides, all these are basic in nature. Now what about this? Amphoteric oxides. These are the oxides which react with acids to give salt and water. They also react with bases and give salt and water. That means they are both acidic as well as basic. So they react both with acids as well as bases to give salt and water. So they are called amphoteric. Ubhaya, eradu gunagalana amphibians we say eradu gunaಗಳು, ubhaya gunaಗಳು. So example, Al2O3, zinc oxide, lead monoxide, tannic oxide, all these are examples for amphoteric oxides. Neutral oxides, these act both as acids and bases, and these no acidic character, no basic character, so they are neutral. Examples are nitric oxide, nitrous oxide, carbon monoxide. These are all neutral oxides. So this is about classification of oxides. So oxides are classified into acidic, basic, amphoteric and neutral oxides. So next we will start with another compound here, or element I can say. It is the allotrope of oxygen, that is ozone. Ozone. When I say ozone, I know you are trying to recall about ozone layer, its depletion, all these things. First we will start with so ozone is the preparation of ozone. Before that, how do we, or where is ozone? It's 20 kilometer height from the earth. There is ozone layer. It is prepared from oxygen by the action of UV light. The action of UV light on oxygen converts it into ozone, and about a very high altitude of 20 kilometers from earth surface. Now how do we prepare ozone? So preparation of ozone, remember students, this is one of the very important questions which has come many times in the examination. How do you prepare ozone in the laboratory? So this is a very, very important method you have to remember. The dry and pure oxygen is taken and silent electric discharge is passed through this. No sparks. Silent electric discharge means the sparkless, because the conversion of oxygen into ozone is an endothermic process. Delta H is positive 142 kilojoules per mole, and therefore because it is an endothermic process, if there are sparks, the ozone gets back to oxygen conversion, the reversible reaction proceeds. So sparkless electricity called silent electric discharge converts oxygen into ozone, that too only 10% of ozone is produced. So 10% of ozone mixed with the remaining oxygen is called ozonized oxygen. So the oxygen along with the formed ozone. That mixture is called ozonized oxygen. So this is how we prepare. Normally it is asked for 2 marks, equation carries 1 mark and the explanation 1 mark. So this is an important concept or question in view of your examination that you have to remember. So this is an endothermic compound. Next, coming to the properties of ozone. It is a colorless, it is a blue gas, dark blue liquid and violet black solid. In small concentrations it has a pleasant smell, but when the concentration increases more than 100 ppm, it is quite dangerous. It causes headache, nausea, etc. Now coming to the ಇನ್ನಿದೊಂದು 5 ನಿಮಿಷ ಅಷ್ಟೇ ಮುಗಿತು. ಕಂಟಿನ್ಯೂ ಮಾಡಿದೆ. ಸೊ ಪ್ರಾಪರ್ಟೀಸ್ ಆಫ್ ಓಝೋನ್, ಫಿಸಿಕಲ್ ಪ್ರಾಪರ್ಟೀಸ್. ಇಟ್ಸ್ ಅ pale blue or blue gas, in the liquid form dark blue and violet black solid, and it is in low concentration, as I have told you, is harmless, but when the concentration increases it is hazardous or it's not good for health. It causes headache, nausea, etc. Next we are now concentrating on the chemical properties. We'll see about the stability. I have told you already, the ozone is an endothermic compound, energy is absorbed and it is unstable due to the increase in energy, and therefore the decomposition of ozone into oxygen is an exothermic process, reverse process is exothermic. And because it is exothermic, it is spontaneous. And one more thing added to delta H is negative, which is one criteria for spontaneity. And if you consider delta S, 2 moles of ozone gives 3 moles of oxygen, so randomness increases. So S2 is more than S1 and therefore delta S is positive. In the equation delta G gives delta H minus T delta S, this is positive and this is negative, therefore delta G value is highly negative, which means this reaction is very spontaneous reaction. Therefore having ozone stored in a large concentration is highly dangerous as it may explode. Therefore to deal with ozone we have to be very careful. Next, this is about stability. Next, oxidizing property. Because it has oxygen in it, it's a good oxidizing agent because it is not very stable. It easily decomposes to give oxygen and nascent oxygen. So ozone is a very good oxidizing agent. What we see 2 reactions. One, it oxidizes lead sulfide PbS into lead sulfate. For example, PbS plus 4O3 gives PbSO4 plus 4O2. So PbS, which is black in color, is oxidized to white lead sulfate in the presence of ozone. It also oxidizes iodides into iodine. So 2I minus plus ozone in the presence of water, it will give you iodine and oxygen is given out and hydroxide ions are produced. So iodides, any iodide when treated with ozone in a solution form gives iodine and oxygen along with the other product. So these 2 are the oxidizing properties you have in your syllabus. And then the third one we are discussing here is threat to the ozone layer. So because of the man-made actions, the ozone layer which was there intact protecting the human beings from the harmful UV radiation which may otherwise cause skin cancer or cataract problem, eye problems, is protected till now, protected. And nowadays it is seen that, nowadays means recently, many years back, it was seen that there are big holes in the ozone layer, which means the ozone layer is diluted and it's called depletion of the ozone layer. Mainly the exhaust gases of supersonic jet aeroplanes contain oxides of nitrogen, especially nitric oxide. This reacts with ozone present in the ozone layer. So this much ozone is removed. And not only this, you know very well the CFCs, freons, chlorofluorocarbons we use in the refrigerators, and then aerosol sprays also are found to damage the ozone layer. So we have to be very careful, and scientists have already planned, or they are in action to prevent the ozone layer by using eco-friendly materials. So that is about the threat to ozone layer. Then the structure of ozone. This also you have studied last year. Ozone this is a coordinate bond and this is a covalent bond. So this is one structure in equilibrium with another where these two form multiple bond, and this is a coordinate bond, and the single and double bonds finally due to resonance have a same bond length, and we represent this as like this. Bond length becomes 128 picometer. Otherwise, normally if there is one single and one double bond, two bond lengths should be different. But due to the delocalization of these two electrons which move from here to here, and therefore this is a resonance structure, resonance hybrid of these two canonical structures, and where both the bond lengths are equal. Now last portion of ozone is the uses of ozone. Ozone finds use as a germicide, disinfectant, and because it easily gives out oxygen, it is used for sterilizing water also, and then for bleaching oils, starch, ivory, ಫ್ಲೋರ್ಸ್ ಹಿಟ್ಟುಗಳು, ಆಲ್ ದೀಸ್ ಕಲರನ್ನು ತೆಗಿಲಿಕ್ಕೆ ನಿರ್ವರಣೀಕರಣ, ಬ್ಲೀಚಿಂಗ್ ಅಂದರೆ. ಸೊ ಓಝೋನ್ ಫೈಂಡ್ಸ್ ಯೂಸ್. ಇಟ್ ಈಸ್ ಆಲ್ಸೋ ಯೂಸ್ಡ್ ಆಸ್ ಅನ್ ಆಕ್ಸಿಡೈಸಿಂಗ್ ಏಜೆಂಟ್ ಇನ್ ದ ಪ್ರಿಪರೇಷನ್ ಆಫ್ potassium permanganate. That's all about ozone. Next we will move on to the next element, sulfur.